Have you ever heard of the term parallel universes? It's a theory that suggests the existence of countless universes that share the same appearance and the same timeline as our own. In these universes, there might be another version of me and you living a life that's similar yet slightly different or even completely distinct from our own. This intriguing idea has long sparked our imaginations. Surprisingly, these parallel universes might not just be a figment of our imagination. Many scientists believe that parallel universes really could exist. What leads them to make such claims? Could parallel universes genuinely exist as they suggest? And if they do exist, what meaning could they hold for our lives? Today, we're diving into the topic of parallel universe theories, specifically focusing on the many worlds interpretation of quantum mechanics, which is among the most supported in the field. According to this interpretation, every event, interaction, or observation in this world causes the universe to split, creating parallel universes where every possible outcome actually occurs. When you face a choice between option A and option B, and you make a decision, the world splits into two, one where A was chosen and another where B was chosen. At first glance, this might sound absurd, but a significant number of scientists support the many worlds interpretation. They favor it because it conveniently explains phenomena in quantum mechanics. But before we go deeper into parallel universes, let's first discuss quantum mechanics. In the microscopic world, where tiny particles like electrons reside, phenomena occur that can't be explained by classical physics. Quantum mechanics was developed to explain these phenomena. A classic example is the double slit experiment. In this experiment, electrons, which are particles, should create two distinct lines on a screen when shot through two slits. However, the actual results showed multiple lines, not just two. This outcome can only be explained if the electrons behaved like waves, not particles. If they move like waves, they pass through both slits simultaneously, causing diffraction at each slit and creating two wave patterns. When these waves intersect, they cause an interference pattern where they either amplify or cancel each other out, creating bright and dark lines on a screen. Scientists tried to observe how electrons move, leading to a fascinating discovery. The moment they observed the electrons, they behaved like particles, passing through only one of the slits and creating just two lines on the screen, as expected of particles. It's as if the electrons knew they were being watched, behaving like waves when not observed, and like particles when observed. Niels Bohr, a leading figure in the Copenhagen school, explained this mysterious behavior with quantum mechanics. He stated that before we observe an electron, we cannot know its exact position. It exists merely as a probability, a wave function, as described by Schrödinger. The moment we observe it, the wave function collapses, and the electron's position becomes definite. This is the essence of the Copenhagen interpretation, which asserts that we cannot know the exact state or properties of an electron before observation, a notion completely at odds with traditional physics. Prominent physicists like Einstein and Schrödinger criticized this interpretation, calling it absurd. Schrödinger illustrated the absurdity through his famous thought experiment, Schrödinger's cat. In this scenario, a cat is placed in a box with a mechanism that has a 50% chance of releasing poison after an hour. After an hour, the cat is either dead or alive with a 50% chance for each. According to the Copenhagen interpretation, until we open the box, the cat is simultaneously alive and dead. When we look inside the box, one possibility collapses, and only one outcome remains. This example, intended to criticize the Copenhagen interpretation, ironically became one of the most famous illustrations of quantum mechanics. Despite ongoing criticism from traditional scientists, Bohr defended his views, and the Copenhagen interpretation became the standard explanation in quantum mechanics. However, some aspects were still unclear, such as what exactly constitutes an observation, and why does the wave function collapse upon observation? Hugh Everett, an American physicist, challenged the notion of observation in the Copenhagen interpretation. According to Schrödinger's wave equation, which is fundamental to quantum mechanics, there is no mathematical implication that the wave function should collapse. Therefore, it doesn't collapse. It only appears to because we observe only one outcome. The other outcomes don't disappear. They continue to exist in multiple split parallel universes. The interference pattern in the double slit experiment is a trace of these many parallel universes existing simultaneously. This is the core of the many worlds interpretation of quantum mechanics. What we thought was a wave function collapse is merely an illusion from the observer's perspective. Just as the electron appears to split into one passing through the left slit and another through the right, the observer splits into one observing the electron through the left and another through the right slit. This splitting of the observer suggests that the universe itself splits, indicating the existence of parallel universes. We can't feel the universe splitting any more than we can feel the Earth's rotation or orbit. Just as we are part of this world, we are unaware of the world splitting. However, there are decisive clues that suggest the existence of a multiverse or parallel universes. The very existence of this universe, with constants like the speed of light, the charge of an electron, and the gravitational constant, hints at it. If any of these constants were slightly different, the entire universe, its laws, and even our existence would be drastically different. Our universe is known to have originated from the Big Bang. But could a single Big Bang have aligned all physical constants within such a narrow range? This is known as the fine-tuning problem. According to British physicist Roger Penrose, the probability of such fine-tuning is 10 to the power of minus 1230, a number with 1230 zeros following a decimal point. It's virtually impossible for the universe to have formed by chance from a single Big Bang. So there are two possibilities. First, this universe was intentionally crafted. Second, there have been as many Big Bangs as suggested by the exponent 10, 1230. If, as the many worlds interpretation suggests, the universe has continuously split from the moment of the Big Bang, then among the countless parallel universes, there's enough chance for a universe where we can exist, like the one we're living in now. The existence of this universe, and our very existence, proves it. If the second hypothesis is true, it has profound implications for our lives. Even if the probability is incredibly low, in some parallel universe, it must occur. If you roll a die, the chance of getting a 6 is 1/6. If you roll it 6 times, you might get a 6 about once, 12 times, maybe twice. But what if you roll it indefinitely? Eventually, you'd get an infinite number of 6s. Likewise, our potential is infinite. Like in the movie Everything Everywhere All at Once, somewhere in this universe, there's a version of you who is a billionaire, a version who is a global influencer. And who's to say that this universe isn't the one you're living in right now? In a universe where our possibilities are infinite, where you can be anything, that's the parallel universe. Despite not being mainstream, the many worlds interpretation and parallel universe theories receive substantial support from many scientists. Perhaps it's because they stir our curiosity and desire to explore, offering infinite possibilities and allowing us to imagine an infinite future. That's all for today's video. Thank you for watching till the end. I'll see you in the next one.